Hello, everyone. So first of all, I'd like to wish a warm welcome to all participants who have joined or who are still coming in. Welcome to this seminar. This is the first seminar of a series initiated by E-SWAN on the important topic of sustainability of our space activities. Actually, this is the working group on sustainability from the E-SWAN Association, who is organizing these webinars. And really the goal of this working group is twofold. First, we want to assess the impact of our activities, the environmental impact. And second, we also want to search for alternative and less damaging ways of working. So 3 webinars are already scheduled, the one of today, a second seminar on October 12 on the future of our scientific meetings, and a third one on October 19 on life cycle assessment of the space activities. Today we will talk about digital technology. We all use heavily computer resources in our research. And so today we will talk about the energy challenge of digital technology. I'm Véronique Delouille and I will be your host today. And it's my great pleasure to welcome Professor David Hill. David is professor at CNRS, the French Center for National Research, and professor at Clermont-Auvergne University. From 2008 till 2012, he was vice president of this university and is also past director of a French regional computing center. He was appointed 2 times deputy director of the Auvergne Institute of Computer Science, ISIMA. This is a French Grande École d'Ingénieurs. Currently is responsible for a graduate track at this university. And so the primary field is software engineering. David got his doctoral degree in 1993 in the field of object-oriented software engineering and simulation. He has published nearly 300 papers and directed or co-directed 30 PhD students. And recently, he supervised research at CERN and began to focus on the sustainable digital technology, including artificial intelligence. He also participated to publication on climate change in collaboration with French colleagues from agronomy. This colleague took part in the IPCC reports and were awarding, the Nobel Peace Prize in 2007 already. With that, I just would like to mention to the participant, if you have questions, please write them down in the chat, in the question and answer tab, and we will go through it at the end of the presentation. With that, I leave you the floor, David. It's up to you.
Thank you very much, Veronique. So now we'll talk about the energy challenge that we are facing with the digital technology and try to see if we can reconcile our technological progress and the ecological transition thanks to AI. But first, let's try to see the impact of the digital technology. We sometimes hear that it is dematerialized, but that's not exact, that's not really correct, because the digital things still do exist somewhere, thanks to material goods like networks. Computer data center, you see here a picture of impressive data center, one of Google data center. There are millions of servers in such data centers, and we access all this distantly thanks to terminal like the video we are having today. The webinar is done thanks to hardware. So energy is a real problem for such data center, and this digitalization, we can see, for instance, the underside of a data center where you see many pipes, and you've got colors, and it's smart to have colors because it gives you the direction of water circulation for cooling such a data center. So what is our digital footprint? If we go back at the end of the 60s, we needed at that time something like 70 kilobytes of memory to enable our first moon landing. And now sometimes, well, not sometimes, many times we have emails up and that weigh much more than 70 kilobytes. So let's observe some other figures. If we want to craft, to assemble, to manufacture a computer, it necessitates sometimes 100 to 400 times the final weight, and even more for a smartphone, 700 times the final weight of a smartphone, which means, for instance, for a smartphone, we need 220 kilograms of fossil fuel to manufacture it. We need 22 kilograms of chemical products, and even a little more than 12 tons of liter of waters. So what we can see is the evolution also on this figure, the evolution of the worldwide internet traffic over 10 years before COVID, between 2010 and 2019, and it's impressive, and the ratio is between the reference 2010 and 2019, it goes up to 12 times the amount of energy consumed for our internet traffic. I hope you can see the red laser pointer that we use. So let's have an idea of the amount of energy consumed at the global scale. There was a study carried out between 2018 and 19. It was supported by the Responsible Digital Institute, and they estimated that it was the impact of something like a seventh continent, with the production of more than 1.4 million tons of greenhouse gases. So this would correspond to the traveling of 1.5 billion of European employees to go to work for a full year, for instance. And we estimate the number of global digital users worldwide as a bit more than 4 billion people. And the mass of hardware that we are currently used worldwide is estimated at more than 220 million tons, 5 times the French vehicle fleet, if we take into account an average weight of a bit more than 1 ton per vehicle. So I give you in this slideshow some links that you can check later if you want to have short video to explain the impact of the digital pollution. And we may have so different sources, so different figures. We have to check errors. In fact, we have to check our sources. For instance, you will find that it is costing 39 grams of CO2 to send an email with a file, attached file of 1 megabyte, for instance. Some other sources will say you need 16 grams of CO2. Some other sources will say you need just 4, and some other 1.8 grams. So just to be frankly, in fact, email is not really the problem source at all, and you can see really the difference between the way that were proposed to evaluate all this, and this is depending on the technology used on servers and also on your computers. If you use a laptop, for instance, there is a chance that your laptop is consuming 800% less than a desktop machine, for instance. Depending on the laptop, of course, you may have a portable workstation, which is consuming a lot. It depends on the type of hard drive that you use. There are still some old hard drives, spinning disks, and they are energy consuming. But the modern SSD or NVMe hard drives, they have very interesting energy consumption, and then your laptop will use its battery for 10 hours, for instance. So depending on the technology of the terminal you are using, there is a difference. On the right, you can see an image dealing about the impact of the carbon footprint of online video. The SHIFT project raised some figures in 2019 and also between 2021. And we can see that such figures are discussed, particularly if we will see later that they say that, for instance, Netflix is consuming this amount of CO2, etc. And of course, there is a huge usage of online video. The demand is increasing, and it is much more impact than sending emails. 3 orders of magnitudes more, 1000x, in fact, compared to email. So email is not really the problem, even if you've got a lot of spam like we all have. Another problem that we have is the rapid obsolescence of the product that we are using. So some recent figures. In 2020, approximately 53.6 million tons of digital waste were produced. The problem is sometimes it was planned, meaning that some companies were using human intelligence to propose devices that will not last too much because they want to sell the new one 18 months after, or maybe faster sometimes. And this is a real problem. And there have been some class action in the USA, mainly against printer manufacturer because they were adding electronics to count the number of pages you print, and they are controlling this to make you buy the new ink cartridge, etc., etc. So there is a real waste of this, and they were an estimation of the total number of smartphones, and they estimated that it was weighing something like 138 blue whales, and each blue whale is between 130 tons or 150 tons. When we will be more on the 5G market, there is really a huge number of very good smartphones with only 4G that could be considered as obsolete. There is also an acceleration of our digital needs. And in fact, the digital transformation was accelerated by the COVID crisis. It has contributed to an increase of our digital tools, and it was really useful at that time. We were moving less and much more using tools like Zoom, like we are using today, or other video conferencing tools. And there was a study to see when we were stopped during the crisis, how many greenhouse gas were we saving, etc., and what was the greenhouse gas at the scale of the world, at the scale of my country, for instance. The share of digital greenhouse gas was 2% in France, and at the scale of our Earth, it is something like 4%. It is more than 4% currently, and it is increasing. It is growing continuously. So to compare with the share of the air transport at the world large scale, it was before COVID 4.7% of the energy consumption for air transport and for something percent of digital industry. So it's a lot, in fact, and it could meet up to 8% in 2040. In 2019, the SHIFT project proposed an interesting studies, and they were looking at our usage. In fact, when we were using energy for digital machines, 55% is the use that we make, 20% for using terminals, 19% for the energy consumed in data centers, and 16% used for the network. The production itself is impacting as well. 70% to produce computers, 11% to produce televisions, 11% to produce smartphones, and 6% to produce the other devices that we need to have ICT. So 40% for the manufacturing is not insignificant. It's really important to take this into consideration to keep our machines longer, to have longer warranties. For instance, if we buy a server, it's better to buy it with a 5 or 7 years warranty, and if possible to use it for 10 years. So let's see the consumption of raw materials when we produce our machines, and let's compare with other devices. For instance, if you want to produce a screen, the ratio between the weight of the final product and the elements needed to produce such element, a big screen, for instance, when you want to watch the rugby World Cup, for instance, some like this, and have large screen, and maybe the screen is weighing 6 kilograms, but it took 2 tons, more than 2 tons to produce such screen. To produce a laptop, it could be very impressive as well. For a smartphone, the ratio is even bigger. So you can see that it is consuming 221 kilograms, but the final weight of the smartphone is 0.3 kilograms. So the ratio is better for a laptop, but the condensation of high tech inside a smartphone makes that the ratio is really high. So the problem is, when manufacturing such devices, we use what are called conflict minerals or blood minerals, and we have child labor. And in fact, to produce a gram of smartphone, it takes 80 times more energy than producing 1 gram of a car. So there are some problems with companies which are not, of course, directly paying what we have seen, but indirectly they have been ranked. Apple was the first to consume such kind of conflict minerals, and Google, then HP, Microsoft, Intel, all IBM, Sony, all the major companies in the digital technology, they need such material. Let's have a look at the main metals that are used for ICT. Of course, one of the main one is copper in red here, and lithium is for batteries, etc. You can see this from a French publication of 2015. Another older publication shows that in yellow you've got like copper and metal, etc. Some silver, many different elements will represent, some of them less than 2% of the total weight of a device. This is, for instance, for a smartphone, and more than 75%, more than 3/4 of the total mass of a smartphone is using the yellow natural resources. So let's now go to part 2. Is artificial intelligence an energy greedy technology? And in fact, yes, it takes a lot of energy for machines to learn, and we will try to explain why it is so power hungry. The training of artificial intelligence models can consume, in fact, a big amount of energy. I will take 3 examples. The first one is language processing AI, now becoming famous since ChatGPT. So this is really generating a lot of carbon emission. Training a model, for instance, will correspond to driving 5 cars over their entire lifetime, including the building of the cars, manufacturing of the cars. I will give another example, which is from Google, Google BERT. bidirectional encoder representation for transformer. We'll use it to train it on a French encyclopedia of the 18th century with colleagues who are philosophers. And in the case of BERT, it was trained with 3.3 billion of words from English books, and also from the Wikipedia articles in English. But it had to be trained 40 times on such data set. And if we compare this to a child learning our language, just hearing 45 million of words at the age of 5, and the child will be able to speak correctly. It is 3,000 times fewer than what BERT is using. So we are not really efficient with our artificial intelligence training. A second example is with regular, I would say, regular deep learning models. They were really famous before the introduction of large model language like GPT. Training such models is really energy intensive. If you have to learn what we call we use what is called a learning pipeline, and it takes a lot of time for the hyperparameters to be set. The tuning of such hyperparameters, it takes a long time, and it also depends on the model complexity. So the energy consumption is important, in particularly if we use convolutional neural networks. They are found as the most computationally intensive, in fact. And the other point is we are training AI models repeatedly. You just don't train once, and this is maybe a greater impact because you want to test so many times, and you train a lot, in fact. And you can also produce machines that will forget what they have been trained for. I will maybe discuss this later in the question and answer about undecidable, the fact that programs like many Turing machines can be undecidable, and machine learning can be undecidable. This was published in 2019 in Nature Machine Intelligence. So we need better practices. We need more energy efficient practices in training to reduce our carbon footprint. The evolution, in fact, of the energy consumption for AI is really impressive. If we deal with natural language processing, which is a tough research project, in fact, it is successful now, but the training of such a model will exceed 1 million of kilowatt hours. So that's quite impressive, with huge machines equipped with more than 10,000 processors. The problem is also you have to pay this bill. We are aware that the price of electricity is rising, particularly in Europe, because it is based on the price at which Germany is paying gas, in fact. So it was completely incredible for many companies in France, because their electricity price was multiplied by 4 or 3. That was kind of protection for people, but not for collectivities, including your flats. If you have a collective property of many flats, it's considered as not being individual, and so the price of the electricity for such flats has been multiplied by 4. So training such a model was the equivalent of 500 tons of CO2 emission for a natural language processing model. And this footprint is equivalent to 500 times Paris-New York return flights, to have a comparison to figures that we may be using on a more regular basis. If we look at the human brain energy consumption, we find that our human brains are consuming much less, a few tens of kilowatts, sometimes only 10 kilowatts, sometimes 20, sometimes 40, for tasks that are much more complex than the natural language translation. So nowadays, why do we say that the evolution is impressive? It's not possible to train such kind of models with just your laptop, even if it is a portable workstation. It would take something like 400 years of training the GPT-3 model. The famous GPT is version 3.5, not version 3. It was released on the 30th of November 2022. It was impressive. So it was the beginning, in fact, of a kind of AI revolution toward these directions, not doing everything, but it's impressive. And we now have GPT-4, which is embedded in Microsoft Edge for free. You can pay for GPT-4 at OpenAI, and with MS Edge, Microsoft browser, it's online with access to the internet. So training the old version would require more than 400 hours of computing on my portable workstation, for instance. So this is shown on this figure. For instance, this is a training of GPT-3, 405 years of GPU equivalent year. And there was a comparison in this paper. I give the reference here. The amount of electricity consumption, 1.287 megawatt per hour. And in orange, we see the tech CO2, which is the equivalent of one round trip Paris-New York of CO2, 552. I said 500 just in a slide before. The exact number was 552 return of flight between Paris and New York. So that's really impressive. And it means that this was 250 times higher than what we expect each European to consume in 2050. Maybe the average consumption in Europe could be something like something like 12 tech CO2. Today, some are consuming less, let's say 8, and the objective by the end or beginning of 2050 is 2 tech CO2. So we have a lot of efforts to do, and of course, this can be done with the increase also in technology. If we look at how many pounds are used for 1 year of American life, in average, it is 36,000 pounds. And the training of one GPU model was 78.4 or 78,468 pounds. And the pound is a bit less than half of a kilogram. That's impressive. Just the training of one GPU model of natural language processing. Another comparison, one training of AlphaGo, who defeated Lee Sedol playing Go, is 440 kilowatt per hour. And Lee Sedol brain would be something like 12 kilowatt per hour. And I'm not sure it is per hour, but we have to check this figure. We can discuss this later. So we are talking about GPUs. In fact, what are they? They are general purpose graphical processor units. They were designed for games to improve the effectiveness of 3D rendering inside games to make them more realistic. And they became very, very successful at doing this. There's a kind of matrix processing, vector processing, multiplying vectors and matrices with real numbers, and they started to be much more efficient than the regular FPUs, the floating point unit inside our current processors, modern processors that are called CPUs. And GPUs are consuming much less electricity for doing such tasks. And they are also now used for tensor computing, and they propose tensor cores inside the GPUs. So they are very useful for artificial intelligence. They were introduced, I can remember this, it was at Austin, Texas in 2008. The NVIDIA company was introducing the personal supercomputer, and it was proposing something like 4 teraflops in simple precision with a single board. So it was not for game, it was not for visualizing 3D things. And indeed, I can, if I'm correct, we could not find the plug for the screen. It was just designed for intensive computing. And now it's present everywhere for AI. So if we go up to what we use now, at that time, 2008, something, they were costing below $3,000, below $3,001 board that you plug inside a workstation. In the picture below on the right here, you can see 4 modern GPU that are plugged inside a server. And each of such GPU are incredibly expensive. They are called Hopper 100 GPUs, H100. It's a massive price, between 30,000 to 40,000, depending on the amount of memory you buy. And the CEO of NVIDIA is calling this chip the first chip which is designed for generative AI. It has something like 14,000 CUDA cores, comes with 80 gigabytes of high memory bandwidth, and the memory bus is impressive. It's above 5,000 bits of memory bus. Let's look at this curve. If we look at this, we can see that there are 2 eras, in fact. The first era was between the 60s and 2012. You see here, first era, and then modern era. With the first era, you can see the slope, and the slope is doubling every 2 years. It's not according, in fact, to Moore's law. Moore's law was not about 2 years doubling. If you find the original paper, you will see, and they changed the perception of this, and then it came to doubling every 1.5 years. So this is something looking like the Moore's law, doubling the power. Here, the y-axis is petaflops per day. So you can see the number of petaflops. And in the second era, which is called the modern era, you see a different curves. So now it is doubling every month, not doubling, sorry, multiplied by 3.4. So much more than doubling every month. So this is what is called a new era for the need in energy, because if you follow this curve, you need much more efficient boards, of course, much more efficient GPUs, but you still need much more petaflops. More and more performances. Let's have a look at the Hopper tensor core. Here we've got a picture of Grace Hopper. I'm a fan, in fact. If I'm not wrong, she died in 1997, and she proposed the first COBOL compiler in around 1950, 1952. And the other point I like is, in fact, when she was working for the first computer, it could be at Harvard with a Mark II or something, she found the first actual case of bug, and she recorded it in our lab book and with adhesive. And in fact, we've got now a picture of this, and the name bug was coming from this. It was a real bug inside the machine, and it was impacting the computing. So there is a supercomputer dealing with climate models, high resolution climate model, which is called Hopper, and another name was given for the new GPU boards from NVIDIA, coming with new tensor cores of the 4th generation. And maybe we don't have time to see this video, but if you want to see it, I give the link, and I also give the reference where they published the introduction of this new GPU board, it's really impressive because it was able to do the training of large memory model like GPT in tens of hours. Let's say GPT-3 would require something like 48 hours. And the generation before the Ampere 100, the computing was lasting days, tens of days. And with Volta, the generation before is in months, even maybe more than 1 year. So that's impressive, the advance that they are achieving with such GPU technology. So let's deal about green machine learning. I will give some references about research papers, and they try to understand why we still need more and more energy. So if we want to keep at the state of the art, to have natural language processing models at the state of the art, or computer vision models or deep learning model at the state of the art, then we need more and more energy. So there are some approaches that we'll try to develop, and it is based on 2 elements. The first element will be model compression, and the second element will be the distribution of the knowledge inside the training strategy. So there are 4 categories, in fact, of approaches to make more green the machine learning process. First thing will be to compact neural networks. Second thing will be to use more energy efficient training strategies. They try also to evaluate the energy efficient inferences approaches, and also an energy efficient data usage. And this will also include model compression and data compression. Spiking neurons, spiking neural networks, and an approach which is more stochastic using the Bayesian deep learning is interesting as well. It is lowering the energy consumption, and it's trying to replicate the brain neural firing mechanism. So it has some of the capacities of regular brains. This has been shown, in fact, by a research at the Oak Ridge National Laboratory, and they introduced a deep spiking neural network, and it is a kind of stochastic process that adds random values, like in Bayesian deep learning. I give 2 references here. This gain is currently discussed. There are some tests at the CEA, the Commissariat Énergie Atomique, and they study this with a focus on the hardware to show that maybe it's not so true that we save energy with this. It really depends on the hardware you are using and the number of iterations you make. So I give 2 opposite information with 2 different research papers, and also the direct access to the paper from CEA. Let's now see how we can reduce the impact of AI. First is cooling. We can use liquid cooling. This is not done everywhere. We still have air conditioning cooling. And water is important, in fact. It is an essential resource. So we can see that by producing a smartphone, we need 12 tons of liters. Producing a gene is quite high as well. 1 hour of video during 1 year will represent 365 liters. And the average in France could be 3 hours of video per day, in fact. It depends on people. For a car, it's consuming a lot, 75 tons of liters to produce a car. Not for this one. I tried this one, but maybe I will be more interested in this one. Just because I will not need to replug, in fact, when we have enough sun, and you can change your battery. By 2025, almost next year, a bit more, we will see that an impressive amount of square meters of water would be used for cooling data centers. This could represent 10% of the greenhouse gases used by the digital machines all around the world. 20% of the global electricity for computer science will be consumed just there for cooling. And we also expect, not next year, but in the year after, 75 billions of connected objects. And in 2025, we may have 9 million data centers all around the world. So let's have an example of a Google data center. For instance, this is on the banks of the Columbia River. Like when you've got a nuclear plant, you place it close to water, so it will take water and reproduce water. They try to give back more than water than they are consuming. For a nuclear plant, maybe something like 30% of the water consumed is not replaced. And the approach at Google is they want to replace 120% of the water consumed. I don't know how they do it, but this is an interesting goal. So in 2021, the average water consumption was something like above 1 million liters, 1.6 million liters. There are some comparisons, for instance, growing cotton and manufacture 160 pair of jeans. So that's interesting comparison to keep in your mind. It's impressive, yes, but if you want to have long grass or for feeding cows, you need this. So there are some comparisons with 17 acres of turf long grass and the production of 160 pairs of cotton gin, and this is corresponding to the operation of Google Data Center for 1 day. I give the other references. You can compensate this by planting, for instance, trees. This is not the approach retained by Google. They started to buy renewable energy, and they produce renewable energy. And in 2020, they injected almost 6 gigawatts of new renewable energy. So that's interesting. And they have a goal, which is also impressive. They want to be neutral, in fact, in 2030. Some interesting approaches to save our water, in fact, is called immersion cooling. I think we don't have time to show this small video. So you have a liquid which is not water, which is interesting because it is not it will not harm your motherboards, the server motherboard that are plunged, in fact, in this kind of liquid, which is able to have the heat transfer. In fact, this liquid is done to achieve the heat transfer like an air pump, in fact, and it is non-conductive. It is safe compared to electricity, and I give the link of this short video if you want to learn more. There are some testing about this in many data centers. They will come with more density per rack, something like 40 kilowatt per rack. In some places, you've got racks with 3-4 kilowatts of production. And the other point is it is recycling the kind of liquid they use. They use this liquid, and this liquid is boiling, and then they take the vapor and give back the vapor when it becomes liquid, etc. So that's very interesting. Another approach is more immersion, in fact. This is a data center loaded with 12 racks, more than 800 servers, and they put such data center below the water. It was 36 meters below water for their second phase of trials, in fact, in the Atlantic, in the Pacific as well. How do we accelerate energy transition? We have seen the energy consumption, but there is another side. AI application can be used to improve our energy consumption. We can use market data, commodity data, weather data. We can use such time series to give correct and interesting prediction to identify where it is interesting to place, for instance, a solar farm or wind farm. This is also achieved with images and video data. It could come from satellite images, it can come from weather data, and we also are able to use smart devices, and this kind of technique is also interesting for coordination. You can improve the usage of the grid, electricity grid, in fact. So it can also be used for accelerating the energy transition. You can take a lot of energy when computing or training, yes, but you can give positive feedback as well. So here is a classification of where application of AI can be beneficial for energy transition. They are classified by data types. First class is for renewable power generation and forecasting as well, optimizing the electricity grid management, also the management of distributed resources, and also the discovery of new materials that are interesting for energy saving. Let's have a look at concrete AI application that will reduce energy consumption. Many examples of AI application, in fact, can reduce energy consumption in many domains. The first will be using AI for having more efficient energy cooling. They achieved this at Google using the DeepMind AI, and they reduced their cooling by 40%. That's interesting. At IBM, they were using weather data, cloud imaging, and machine learning to have renewable energy forecasting for wind farms, for instance, and also for solar farms. We also see some optimization. In fact, if we place AI as a domain, operation research is a subdomain of AI. In fact, and inside this, you have simulation and some of the scientists in the weather and climate, space and weather, you are doing a lot of simulations, in fact. So they were using an AI model called PAVE 360, and they simulated the performance of electric vehicles, and they were using AI as well. In the innovation sector, the discovery of a new material at MIT, they were discovering a new kind of catalyst that could split water into hydrogen, oxygen more efficiently, and thus producing hydrogen that could be used as an energy source as well. So it was a clean energy production approach with new material. So the question is, will such efficiency really save us? It depends, not our way. Maybe some of you know what is called the rebound effect in economy. So in fact, the new performances are all sometimes or most of the times accompanied with an increase in the intensity of consumption. We have seen this, for instance, when we went from the 3G for smartphone networking to 4G. 4G, in fact, was really impressive to use video with the 4G. In fact, online video market was taking off thanks to 4G and the smartphone. There are more access to website with smartphone than with computers. With 3G, it was not so current to have good video on smartphones, and with 4G it became used on a day basis and with maybe hours of video consumptions. I give some references here, this kind of study. And what is rebound effect is you can save energy when you go to 4G from 3G, so you save money, and this money is maybe used to more heating, for instance. And if it becomes cheaper because you got a clever usage of your energy for your house, then the money you are saving will allow new devices to be used, gaming, computer, etc. And you're saving again money, and then you will use it to use flights to travel, etc. So this is called the rebound effect and is known in economy. let's see the impressive growth of the digital video. We were using analog video cassette and digital then video with DVDs. And once you buy the DVD, it takes energy to craft, to manufacture the DVD, but you've got it and you can use it many times. When video are stored in data center, they are transferred to us on demand, streaming request. But you do this many times. If you want to re-see the same video, you may have downloaded it, but it's quite rare. Most of the time, you use the link and you use it again. So the resolution increased. Our old television, the resolution was set 240p, around 352 by 240p pixel. The second number is the dimension of the video, and 360p is dimension of the last analog TV we had. For home cinema, we have the 480 pixel, then HD ready, which comes with 720 pixel, then full HD that we have on many laptops now, 1080 pixel, and much more with retina screens, etc. So this kind of resolution, you may find this on some retina screens, is called 4K with 2106 pixels. And if you go up to 8K, you see the smaller number at more than 4,300 pixels. So the volume of data transferred, if you compare with our original television, has been multiplied by 97. If we look at such figure between 2016 and 2021, we use this to see the evolution of the CAGR, which is the compound annual growth rate. You see in light blue the increase of the internet video between 2016 and 2021. Impressive CAGR growth rate of 67.4%, 24% per year. So you start with 50 exabyte per month in 2016, and you go up to almost 200 exabyte per month in 2021. This is the source is given by Cisco networking. So the energy impact of the video is impressive. If we study at the world scale, it could be the equivalent of a country like Spain with something like 300 of megaton per CO2. And with Netflix video service is equivalent to a country like Chile, for instance. Of course, they contest a company like Netflix, they contest such numbers. The debate is open. Bad usage of video. Addictive design. What is addictive design? Addictive design is a small video that you see. For instance, on this smartphone, you see a small video here. You have not requested this small video, but you have been connected to this site, and this site is giving you this small video. This is designed to increase the metrics linked to the website, and this is also linked to advertising revenue. So the more video they give, the more money they will receive, in fact. So this is a kind of antithesis of the idea to have a sober usage of digital technology. There are many approaches to reduce our footprint. In fact, the footprint can be reduced if we reuse, like Back Market was a French initiative, and it started to be now present in 14 countries, giving a second life to many devices. We can see interesting research also, the planned obsolescence and the class action in the US were successful. They gained against Epson, HP, etc., gaining millions of dollars to complainers, in fact. But in other countries, we don't have this mechanism, and we still pay for laser or ink cartridge with excessive margins, in fact, impressive margins. And it was pushing companies to crime, and such margins are discussed now. The other approach is, of course, recycling and creating jobs for having a more sustainable approach. And as a conclusion, AI is really a powerful technology. It can help us to solve many problems, but it has a significant impact on the energy. And its impact is in two ways. One is negative, as we have seen, but also one is positive. We have seen that training requires a lot of computing powers, but we also, in fact, showed that we can optimize energy consumption, and the grid, electricity grid can be more efficient. The cooling can be more efficient. We can also use more low carbon sources. So there are also some interesting and positive impact. And I give you also some links to have more information with small videos, for instance, AI versus climate change by Dr. Adam Levy, who has a PhD from Oxford as a climatologist. Thanks for your kind attention. I'm now ready for questions.
Thank you, David, for this very interesting view on this question, on the impact, and on also what can be done to reduce this impact. We have one question already. Please, to the attendee, if you have questions, you can write them down in the chat. There is also one hand that is raised. Yes. You can also ask it live. So the first question by Jean Lillenstein is actually webinars like this one. They also consume energy. Do you have an idea what is the energy consumption of this webinar? And more generally, a lot of effort are spent to organize kind of exchange using webinars, and the multiplication of webinars throughout the world is another rebound effect, isn't it?
Yes, it is, in fact, but we have to keep in mind the real impact. So if we look at the energy consumption of 1.5 EDO every day during a full year, we have figures that we have seen just here, for instance. This is the amount of liter. I don't know in the equivalent of CO2, but it means watching 1.5 EDO every day for 1 year. So you can see that its impact quite small. I'm not sure that we have a huge impact with such webinar. Maybe we have 5 attendees. No, it's something like 30 maybe, or 26. I see 26 participants. So you can really compute. We could compute this. I think becoming more aware of such problems could be interesting to reduce our footprint. So of course we could say just don't communicate, and the organization will just use a few emails. And as I said, the few emails is 3 orders of magnitude smaller than the video. So the video impact is impressive, but maybe watching TV series with high resolution, and this is not the case with Zoom. It uses compressed images, etc. So I think it's worth it. I think it's worth it. And yes, we may reply to other questions.
Yes, so David,
it is a rebound effect. Yes, it's true. It's true. The second question I can from the same person. It is an example of rebound effects. That's true.
Okay, David Berpans, you wanted to say something? Normally you can unmute yourself. No?
Yes, sorry, can you hear me?
Yes, I can hear you, yeah.
Thanks for the very interesting talk. That was really inspiring, and we'll have a lot to chew upon afterwards. Quick comment to Veronique, the chat is disabled. We cannot write chats.
No, it's in the question and answer. You have the Q&A. That's
okay.
the chat.
And I see three questions, and a question from Patricia.
Okay, sorry. My question was on slide 23. If we
we can move to slide 23.
So it says that it's the increase of energy needs, but the vertical axis is in petaflops. So
23. 23,
yes.
Sorry. 23. Vertical axis is petaflops per day.
Okay.
Which means something like 10,000 petaflops per day to train AlphaZero, for instance, AlphaGo 0.
Yes,
it's impressive.
These are astronomical numbers.
Yes.
But my question was, from over this time range, the petaflop has hopefully become
Cheaper.
Cheaper in kilowatt hours.
Yes.
So would it be as dramatic if we would have the vertical axis here in kilowatt hours?
No, it could be interesting, or it could be interesting to have it in CO2. So I was taking this picture from, I think it was Conversation, and I give the link just before, maybe, or after. So I was not managing this data myself. I took this picture from a study that was published in Conversation. You know, the journal, which is in English and in French. So.
Thank you very much.
You're welcome.
So you see the question of Patricia Lampens, a very interesting talk. Lots of figures are given. How can education of young people help with the excessive usage of AI tools?
That's very interesting as a teacher. So, of course, we teach not only in university or engineering school, we also teach sometimes or give conferences in college. Maybe there is an excessive usage of AI tools like GPT because it is helpful for children when they are doing their homework, for instance, except that it's creating sometimes wrong data, wrong information, because it is creating based on a lot of information. The AI is not proposing also the truth. It's difficult. This is interesting to see the approach of Microsoft, where with being GPT-4, you can have a more creative answer or a more precise answer. And we know that it will not come with the truth. It will come with a probabilistic or realistic answer with high probability, but it's not truth. So for many questions, it can be really imprecise. I think that they will learn it by themselves if they got bad marks at school, for instance. So they will realize that it is not the right tool for doing this. Maybe there will be huge progress in the next few years, and they will come with, like Elon Musk was saying, Elon Musk was saying, we want a truth GPT. I can't follow Elon Musk for many things, but I can follow him for this. We need a truth GPT. It is very useful. If we can have a truth GPT, we will try to build for the philosopher GPTs dedicated to the old encyclopedia from Flaubert and other philosopher of the 18th, plenty of the philosopher of the 18th century. We've got the source. We want to train and to dialogue with, in fact, with the knowledge at this time. This is interesting if you are studying history or philosophy, not for everybody. So maybe there will be an increase of usage of AI tool. I don't know when it will be excessive. Maybe the usage is excessive with video. They are passive watching videos, and sometimes losing their time with this and addictive video. And some companies are using their brain to make them more and more addictive. So maybe you know the film which was called Social Dilemma. With the short, I'm not using social networks. They are always on social networks. And so they share images, they share video, and they take a lot of their time watching videos. I don't know how to stop this.
Mm-hmm. Okay, well, we have another question. So
Yeah.
From Françoise Humble. I think a big issue is that today digital technology users ignore the amount of resources and energy they use. do you see a way to make so that final users can no longer ignore the impact on resources and energy? And final users is like us, no?
Yeah. It's final users. Yes,
Researchers.
Everywhere. Us, we are final users, and even in labs, even in computer science labs, not all of our colleagues, they are aware of this. Maybe we would become aware if we have to pay a more expensive price based not on gigabytes but based on CO2. I don't know if we really want to reduce our footprint to something like 2 tons of CO2 per year or something like this. It's kind of quota. In fact, like you've got a quota to use your supercomputer and you get at least 5 hours per month, and that's costing a lot, so you don't want to buy more. Maybe it could be a way to make them realize, and I'm not sure they realize, it's like buying gigabytes on your contracts for your smartphone. I'm looking at what I'm consuming. So I know I'm consuming between 20 and 50 gigabytes per month. Maybe it could be too much for plenty of my students. It's very small because they are playing games, and maybe they need 160 gigabytes or more per month.
But maybe talks like this one are already something that make people aware that when we use computing resources, when we use deep learning, etc., this comes with a cost. Do you think that, so for us researchers, putting some time on improving the code, the efficiency of the code has a significant effect?
Yes, it has. Optimizing the code is really important. For instance, I'm sorry, I will discuss of personal experience. I noted the indications that we should not talk a lot about this, but let's talk about experience with colleagues in physics. They were building a model to simulate a scanner experiment for a person for detecting small tumors, etc. So they were using tomography and reverse methods, etc. And they had an interesting approach with Monte Carlo simulation. It was much more precise than the analytical method to detect tumors with a size below 1 centimeter, except that the analytic method was lasting 2 seconds. And but with 100% of error for small tumors, and the stochastic model was able to reduce the error for small tumors just to 10%, and the computing was lasting 9 hours. So they thought they will be stopping the PhD thesis, and they came to us to optimize their code. And in this case, we could get an impressive optimization if we divided the time by 180 by using the right hardware and some optimization techniques, different kind of storage, compression, etc. And we were giving the result in 3 minutes instead of 109 hours. And of course, they had to achieve this kind of computing many times to get good statistics. So the PhD started again, it finished correctly, and now we have a colleague who is a research director at CNRS. He's 42 years old now. But this is an example of how optimization can save your money, your electricity, and instead of having a cluster with 200 processors working for you, you've got just one server and is with a single core that will do the job.
Yes, yes. So it's really worth to invest time.
Invest on the method you use. Optimizing. This is a kind of research that we do in computer science, in fact, and it's not so easy. And you need not just geeks, fine geeks. You need a nerd. You're really a deep geek to achieve this kind of aware of the hardware, aware of the languages, the software stack, etc. And you can have gain. Yes.
Okay, final remark by Patricia, who asked about the education of young people. She said, well, the teacher should help in this decision taking. When is it useful to use ChatGPT, when it's not, etc.
Yes, we can educate. Yes, we can educate and show that in some approaches it's useful, in some other it's a waste. I have seen in French reports to help teachers how to use GPT or BART or BERT, etc., to improve your teaching and make the students aware, or the young children at college to be aware of what they are doing. But it could change maybe in the next 5 years. So it's difficult to cope with the pace that the digital technology is giving to us. In fact, we have to follow. Most of the time we have to follow. We are not all scientists in AI. I'm not, in fact, even if I use it, it's not so easy.
We have another remark by saying, as a scientist, I'm afraid that optimization always comes with a rebound effect.
Yes,
Very
yes,
often
that's true. Yes,
yeah.
that's true. Yes, yes. In fact, if we have a faster model, we will make more experiment. And this is the main reason why we still need bigger and bigger supercomputers. When we do the design of the experiments with all the factors, we want more levels for all the factors. So we always need a bigger machine. We are always unsatisfied because we want to increase the resolution. I completely agree with this. Yes, it will come with a rebound effect. Yes.
Okay, so thanks a lot for all these pointers, all these links. As David said, we have a lot of things to think about. So thank you a lot for this very interesting discussion. And so I remind everybody that there will be a second seminar on the problem of our scientific meeting, the future of our scientific meetings, on the 12th of October. And 1 week after, on the 19th of October, a person will come to explain us the life cycle assessment of our space activity, of our space infrastructure. Thanks a lot for participating into this webinar. Yes, and all the information are on the calendar of STC. Thanks a lot for participating, and have a good afternoon. Bye.
Thank you, Veronique. Thank you all. Bye-bye.
Bye-bye.